Welcome.
All right, I started the recording. I'm going to turn it over now to Dr. So to introduce our speaker today.
All right. Thank you everybody for joining the Zoom seminar today. We have Dr. Jaehun Chun, who is the Senior Research Scientist at Pacific Northwest National Laboratory. He has been there for the last 12 years. I met him for the first time last year during UACHE. So I talked to him. He graciously agreed to come to BYU for this seminar. But unfortunately, you know what happened in March this year. So unfortunately, we are having him here at the Zoom. But sometime, I really hope sometime I can have Dr. John in our campus. So I told you that he has been in the Pacific Northwest National Laboratory for the past 12 years. He's also an affiliate professor of the Levitch Institute in the Department of Chemical Engineering at CUNY, City College of New York. He also received a PhD from Cornell University, studying colloidal dispersion. I don't know how many of you heard about colloid. Probably he's gonna talk more about colloid today. And he received numerous awards. Probably it's too time consuming, so I'm not gonna talk more about his awards, but he's one of the R&D 100 award in mechanical material category. So you can see that his research achievements are stellar. So I want you to everybody welcome Dr. John. And Dr. John, please, thank you for joining this seminar again. So please start your presentation, please.
Okay, thanks for sort of like a very kind introduction. I think he presented sort of like a more than what I should be. Yeah, thank you. So it's my pleasure to give a talk. I really hope to give a talk in person, but it's unfortunately this situation, this is sort of the best, but I can actually take a flight seat instead, which looks great in the background. So I'm going to talk today about the colloidal dispersion. So it's giving you some idea about the colloidal dispersion and some forces. So then based on my ongoing researches and previous researches, so then how they actually length scale, all length scale are correlated. So that's sort of like a basic sort of the concept and philosophy. So let me see, it's not, yeah. So as you see this, the colloidal dispersion is pretty much sorry, this is a bit slow. The network is not very fast enough. So colloidal dispersion is essentially all around us. So as many of you know, so then is involved in various products like food, and then and also the cosmetics, and then there's the essentially like healthcare products, but also involved in many industrial processes is like the semiconductor processing is such as you see, sorry, I think it's better to have like a pointer, yeah, laser pointer. So it's like an industrial process, semiconductor processing. Also there's the bio and other application is also involved in the quantum dots here. You see the beautiful colors here. And also these ugly picture is about the Hanford waste tank picture, which is where all the slurry and sludges in the tank. So it's actually also a lot of environmental issue involved in associated with colloidal dispersion. So you see here, the colloidal dispersion is very sort of simple. So you have particles, and then you have a particle called the dispersed phase. That could be typically either solid or liquid. And then this continuous phase is typically in the liquid, but that could be in another type of solid. There's various pairs in terms of colloidal dispersion. The broad definition of colloidal dispersions is as a pair of solid liquid, solid gas, air liquid type of things. So the bubbles and all the foams is also under this category, although I didn't actually put that very specific. So the colloidal dispersions here, so have like also involved in very industrial processes. So like for example, this one is about called the electrodeposition. So we actually use the charges particles here to apply the voltages and to produce the coated area for these kind of with the properties of interest. And also involved various natural process, which I'll show you. One thing I showed that later for crystal growth. This one is called the colloid facilitated transport. So where is some kind of the pollutant or so for example, radionuclide deposits onto the colloid in natural space. This is actually subsurface kind of pore transport environment. So they put in the colloids, and colloid is actually coming through that the fluid flow. So these colloids is actually much higher speed than the typical fluid around it. So then the colloid is actually main cause to these, like for example, the pollutant. In this case, for example, is the radionuclide is actually transport much farther distance. So how to actually understand this colloid interaction with the pore surface, and then how this influences charges of the pore that with respect to the transport of the colloids, and then how these the pollutant absorb in the colloid. Those kind of things all is under the colloidal dispersion, and then sort of like ongoing researches in the geological space. So there's all various kind of the environment or there's this substance or let's say the context involved associated with colloidal dispersion. In some cases, I already showed this, we actually use the rheological properties, such as viscosity and then the yield stress on some kind of the rheological properties to really produce ideal or desired product, such as this honey and there's the foams. Foam cannot really like a flow through, right? So have some kind of shape. So really like a fundamental details involve how to make this, how could we actually make them flow, but it's not really like a too thick in comparison to the too thin. So it's like a really the control of the process that all involves like a particle forces and colloidal kind of principles in colloidal dispersions. So you see the colloidal dispersion, you typically see this kind of the particle based, so the particle interaction. So you've seen the couple of people as we've already known about this phenomena. But as you do see the later in my talk is associated with how they actually aggregate, because that's the essential result from the particle interaction. How this aggregate influence the macroscopic rheological property, which I just showed that non-Newtonian, Newtonian, yield stress, those kind of things. So then actually dealing with very large length scale. But on the other side, if you actually, there's the interfacial chemistry and water structure around the colloids, that actually influence the particle interaction. So you see here from the nanometer scale up to millimeter and larger scale. So those length scale and different phenomena are really coupled each other. So the multiple length scale, which I just exemplified, but it's also time scale is actually heavily involved here. So it's somehow the colloidal dispersion is natural or intrinsic multi-length scale, time scale is actually phenomena, is already implemented. But is actually the key here is actually these all connection we can actually understand as using the bridges. Here, bridges here is particle interactions. The particle interaction is actually a way to connect these very nanometer length scale, and then there's the millimeter and there's a larger aggregate scale is eventually connecting to that the macroscopic scale. So the interaction here is colloidal interaction, typically the physical chemical interaction. So colloidal interaction, the van der Waals interaction and electrostatic interaction. There is also hydrodynamic interaction involved. And there is another type of interaction, which is the mechanical interaction, which I'll actually touch a little bit about the friction between the particles. So those are essentially the interaction we will actually touch a little bit. So then so they're starting with what we know about the particle interaction. The particle interaction we know is first electrostatics. Electrostatics is essentially all about charges, ion interfaces. So when you have charges in the interfaces, So that is actually opposite charges is more attractive to that surface. And whereas there's the co-ion, which is the same charge, is more sort of repulsive. That actually creates some inhomogeneous distribution of ions around this, near the surfaces. These inhomogeneous distribution obviously is different from this, the bulk, which is no surface, is far away from this surface. So those difference, distribution is actually giving some osmotic pressure due to the distribution, different distribution of ion. So that actually is really the origin of the electrostatic interaction. Because of the typical nature of osmotic pressure is a positive, so there's the pressure is positive pressure, so that actually gives some, typically electrostatic interaction is repulsive, so the repulsive between two surfaces. Another one is actually the van der Waals interaction. So this is all about the electromagnetic fluctuation. So how they actually electromagnetic wave fluctuate and then interact between the two surfaces, which is so-called modern view. So these body colloids creates the electromagnetic field because of this, the electron motion in the inside. So, but there is actually very different frequency ranges. Same thing here. So then they interact each other. In some frequencies, they interact so like a positively, some cases canceled out. So this is sort of like a very analogous to the two big boat and ship interacting with each other in the sea under the water. You've already kind of noticed that somehow, some kind of already knew that the ship is interacting with because of wave here. So they're very analogous kind of the picture in this case here, but it's starting from this van der Waals. That's why this called the van der Waals interaction. So what is actually interaction between neutral molecules? So the people didn't know about that. So then after that, this is called the very famous van der Waals state of the equation of state. So this is about this term. This is actually related to that the interaction term somehow. So then people after that, this is about the dipole. So then dipole could be permanent dipole depending on the charges or balance of charges of molecule, and then keep fluctuating. That's its origin. That could be origin of van der Waals forces. So using that concept, this attraction between large particles could be calculated using this called as the fluctuating dipole or London potential, the integrating over two bodies. So the first people who have done this is actually the Hamaker, which that's the name as the original name of Hamaker constant in van der Waals force in every textbook for the colloidal dispersion. So then Hamaker constant really is like a material properties. So which one is in the system? So then polystyrene, the gold and silver is also different in vacuum and water. So this is really a strength. So there's sometimes the large values of this, they actually attract more, that the less value is actually the attracted less. So this is about the van der Waals interaction. So if we have that is the electrostatic part of that, which I just mentioned, and then the van der Waals part of that. So the combination of this, that is typically the very conventional, very original, the DLV theory. It's the Diogen, Landau, Voigt, and Overbeek theory. So these kind of the theory is relatively simple. So that's why this applied to has been applied in many the systems and the phenomena to understand the colloidal stability. So you see the picture in the Israel Chivelis book. So then there's charges, how that charges changes stability, and then how that is van der Waals interaction influence that. So those are essentially the nice, conventional, the framework. But another thing which typically is missing in that previous one, the two things, van der Waals DLV theory is about energetics. But it's, when you talk about particle interaction, because particles keep moving, there's also another part is called as we call this the non-equilibrium or the dynamic part of that, which is related to fluid mechanics, so-called hydrodynamic interaction. The hydrodynamic interaction happens because the velocity, when something particle is moving, these velocity creates the velocity disturbance around here. but that disturbance is really long range, decays at the 1 over separation. So because of that, these motion creates influence in another particle depending on the particle separation. And this motion is also influenced this, so then back and forth. So that actually is the very origin of the hydrodynamic interaction. Obviously, if there's no particles here, such as this case, is Stokes drag. But here, there is a Stokes drag with multiplied by some factor, which we call the hydrodynamic interaction. So one of the best example for hydrodynamic interaction is the lubrication force. The lubrication force is something they actually repair each other because they actually have a large pressure built when they close each other. So they actually prohibit the motion between two particles. So those combination of the hydrodynamic interaction and the electrostatic van der Waals, that's basically what we've already known from the typical textbook. So what I'm trying to tell you is a little bit beyond that. So they're using how the microscopic details, such as molecular details, how that influence the particle interaction. And typically all I showed before is spherical particle, right? But it's actually in reality, spherical particle is not all the cases. In fact, many of the cases, especially get down to mineral nanoparticles, and then quantum dots and other, it's not really like sphere. They have a shape, some kind of the rectangular shape, and some cases actually cube. So how those shape influence interaction and aggregation. And then another last one is how those interaction, because we still actually, how those interaction and surface roughness is actually changes the rheological properties. So those are essentially some examples based on my researches with collaborator. So then these all kind of details and motivated by this so-called the collective phenomena. So one of collective phenomena is called the oriented attachment, which is about this crystal growth. Then crystal growth area, what people know that these ions and atoms and molecules added one by one to create the bulk crystals. That's been known. So then called the monomer and monomer crystal growth. But however, recently, like around 2000, the many of group has found that, no, that's not the only pathway. Another pathway is, first, this one is ion atoms and molecules formed in nanocrystals. And then those nanocrystals aggregate or self-assembly, which they called oriented attachment. But this one is why they call the oriented attachment, because they keep maintaining crystal phase is actually keep maintaining same crystallographic phase. So which means that they actually keep aggregating or keep doing the self-assembly, but while maintaining the crystallographic axis growth. So then it's actually really aligned. So that's why I call the arrangement to make a bulk single crystals. So this one is unique. From my point of view, so that like a colloidal assembly point of view is unique nanoparticle self-assembly, which about including orientation. But this one is size of this about 3 to 5 nanometer. So that's actually already somehow brings some idea, oh, maybe like some details, molecular details, ion size, or some kind of the structure, those details would matter for this type of the assembly or crystal growth kind of pathway. So then is actually question is how to understand these specific, very small size particle interaction. That's actually one motivation of this. Why do we care about these details, coupling between scale? Another one is actually a handful Waals slurries. If you see that, probably you've already heard many of these handful Waals slurry, but it's actually this one from the point of view and from the person like me, like a colloidal scientist, is about very unique colloidal dispersions. The unique because of the very high ionic strength, typically sometimes more than 1 mole, and pH is about 13, at least 10, and then broad size particle distribution. If you see this, have like sometimes like a submicron to the really like 100 micron, but it's actually a very challenging part is irregular shape. You see, this is one of the baumite. There's actually low mag TM. Oh, that's actually, yeah, TM picture, but it's like really sharp edges. And also interesting thing is actually the high resolution, if you have a surface because that's actually the very intrinsic nature of the mineral crystals have a steps on it. So unlike a mica, which is very, very flat and smooth. So then also there is a radiation field involved, especially because of this, the nuclear waste nature. So then see here, there's the, if you measure the viscosity, so-called the rheometer, you see the shear stress versus shear rate, you do see some large values of the yield stress called. So that if you plot the yield stress as a function of solid, how much the solid particles in it, so it's not really, cannot tell anything. So you see the large spread of the weight of solid. So this is not the only way to look at it. So that one, we can actually see that how these details like shapes, surface roughness, and even the radiation part, and then also the pHs, how those is a role of this kind of a complicated nature on the aggregation in rheology. So those are essentially the good the motivation what we are doing. The first one I'll touch that is actually microscopic details. So then this solution, if you actually consider the surface, solid liquid interface, in this case, minerals. So people found that from the X-ray reflectivity measurement. So then there's different surfaces, muscovite, calcite, rutile, the graphene, they have some kind of the fluctuating layer of the density of the water. This is water densities. And then later on is about the plateau, which is typically what we know, 1 gram per centimeter cube. So these ones, but it's a pattern here is depending on the what surfaces, which is also depending on charges on the surface, which means the pHs and then concentration, and this property of the solid. So then, but it's actually the one common thing is all different patterns, but is actually more or less this interfacial water layer that is about 1 nanometer, something like that. So then is actually things is actually having in some kind of this question having in our mind is for nanoparticles we talked about, in our case, OA case. So the particle size is about 3 to 4 or 5 nanometer. So then that means that interaction between particles becomes important about the separation about the particle size, but it's actually that then is about 4 to 5, 3 to 4, 5 range. But this is interfacial water layer, which is quite different from the bulk water. That is about the 1 nanometer also. So then is actually one thing we can actually think of is, oh, this interfacial water layer is not completely negligible for this case. So that's actually the idea we actually tackled to understand the difference or changes in the interactions. So what we did is so they call the microscopic detail to connect the particle scale. So then these structures, interfacial structure, how they influence the force. So then to do that, we actually sort of very elementary approaches, simple, but it's elementary approaches. So we need to actually modify, we're working on that. So using this density fluctuation near the interface, which is about 1 nanometer or so, which depending on mica, TiO2, and gold. So we use 2 ways. One is the mapping, basically mapping this density fluctuation into properties. In van der Waals case, the relevant property is dielectric properties as a function of frequency. So we actually use these Clausius-Masati well-known equation to map this density profile, which is here, and into that is the dielectric functions. And another way is actually for electrostatic part of that. So we use the Onzegas model, which is there is also densities here, and then the mapping in the dielectric constant here. So using that for van der Waals part, we actually modify this lift shift theory. So we call the modified lift shift theory. Another one is for electrostatic one, we actually modify the Poisson-Boltzmann equation. Poisson-Boltzmann equation, typically we don't have here this term, but now we actually, the dielectric constant is a function of the separation. So it's a variance in dielectric properties. So using that nature, So what we can do here is we actually calculate that. So you see that typical, the conventional DLVO theory is still as very repulsive here, but is actually using this structure, we do see some kind of attraction becomes a repulsive and attractive around that 3 nanometer. So this is sort of like a qualitatively consistent. This is for the mica case from the surface force separation measurement, jump to contact distance. So whereas the DLVO theory, conventional DLVO theory cannot really explain this. So then from that, we do see some importance of this consideration of this, the interfacial structure into the particle forces. Another one is actually we actually collaborate with this, the experimentalists using called the AFM-based Dynamic Force Spectroscopy. So this is sort of like a colloidal probe AFM, but its difference is this. Rather than putting the colloid here, we actually putting the mineral surface, in this case mica, some attached in it. You see this here, and then substrate is also mica. So then what we can do here with this configuration, we can actually measure mica force. So using this pattern, so that we can actually measure this, the adhesion or rupture force between 2 mica. First one is jump in, and then we actually measure the force during the pinch off process. So actually measuring the adhesion between 2 mica surfaces, we could get some idea about how this microscopic detail matters. So here is actually some kind of very the brief key experimental results. So you see here, there's the force as a function of salt is not really monotonic as compared to that is the expectation. Another one interesting is actually we do see the difference in the adhesion force for 2 different ions. So the ion specificity, calcium versus magnesium, which is +2, but it's actually have a different the adhesion force. And also the same thing for the sodium and then potassium, which is the same +1 ion, but it's actually a difference in then the adhesion force. So what we are actually seeing here is this. So the adhesion force we actually see here is 2 mica surfaces, right? So that is actually, we have between them, because the mica surface is negative, we have sort of like a hydrated ion. So then ion here in the microscopic scale, every ion is going to be hydrated by water. So then this cation here, which is actually preferable, having the hydration shell. So these hydrogen shell, we do have this kind of behavior. So that means the separation where we actually measure the adhesion force is not really the solid touching. It has a effectively separated by about 2 layers of hydrated ions. So in this case, these ions could be sodium, potassium, calcium, magnesium. So here is actually the ion specificity in this simplest picture came in. So this positive ion, each one has a different ion sizes and also different hydrated nature. So because of that, it's effective, other than just like a Poisson-Boltzmann way, is valency changes, but also changes in that this hydration layer, this effective, the separation is changed. So another important one is to actually having this, this picture is this. So these one, so if you imagine there's the mica surface close each other, so then there's actually to make the closer, then compared to this case is actually, you actually need to dehydrate water first, right? On the ions. So these dehydration is actually requires huge energies, or the pressure or force, or whatever preference you have. But it's that force, for example, is much higher than force exerted by AFM tip. So then it's typical, the AFM tip is actually cannot really dehydrate these bunch of ions, is actually hydrated. So we actually sort of order magnitude calculation, which is this. The AFM is much smaller than the ion desolvation, so it's called the dehydration. So that is actually, we sort of like a physical the physical rationale is, this is actually could be the the effective size. So that is actually, as I mentioned before, a lot of the positive, negative, and that one is actually the coming in depending on the ion specificity. So then is actually using that. So this is sort of like a details on it. So we could actually expect, or we could actually sort of predict, although it's not very, very qualitative, is actually this non-monotonic nature. And also we could also the sort of explain what is actually the adhesion force as a function of the ion specificity and then the valency. So that's essentially what we are doing in this paper. So that's actually the good combination between experiment and then some simple theory. It's not actually complicated though. And another one is about the shape. Shape is also quite matters. So I'll actually walk through somehow briefly. So you see this is a bomide. Bomide, as I mentioned the previous slide, a couple of slides before, has a shape in it. So then this actually crystallographic axis is aligned in it. So then this is a really shape. So if you do that, understand the aggregation phenomena, or so then what we can do is typically using a DLS, right? A DLS and changing, because this bomide is about PGC is about 9. So then if you have a low pH, we have a positively charged, and higher than that, and then negatively charges. So then we can also play with the salt concentration. So as you see that adding less salt, they actually repel each other. So then actually reaction limited, which means that so they actually having a lot of time to actually aggregate. But whereas we're putting a lot of salt in it, so the diffusion limited, which means that interaction becomes really decays, the repulsion decays very a lot. So then when they actually diffuse enough, so then they aggregate immediately. So we could do the same thing, and then we can actually identify diffusion limited regime and reaction limited regime. So that's actually very similar, but it's actually interesting part is coming from here. So then particle shape, considering particle shape compared to sphere. So what we see that is there is the two diffusivities when the particle is non-spherical particle. One is translational, which is normal, but we also need to consider rotational diffusivity. So then we actually calculate using some kind of called the BEST kind of the software, which calculating hydrodynamic diffusivity mobility software. What we can find that is translational, rotational motion is coupled. As the time scale is not actually far away each other. You see here for these as typical real images. From real images, we map it, we actually make it, and then we actually calculate the translational diffusivity and rotational diffusivity from this configuration. So what that means that these particles, real-shaped particles, is moving diffuse translationally at the time they rotate. So we need to consider, oh, there is some kind of rotational component we need to consider for that particle interaction. So to do that, this is actually a really complicated shape. So we actually use some kind of the cube shape, which is something like this. So then we actually found that this shape of the two, this anisotropic nature, we actually have because of shape, this interaction is also anisotropic. And this is the two interesting mode. When they actually see the face-face, the van der Waals interaction is scaled as 1/, separation square. And then hydrodynamic mobility, how they actually move fast because the lubrication related, is actually mobility is actually decays really like a separation cube. However, if we actually have a vertex, this kind of configuration, van der Waals is actually scales is 1/, separation, which is scale changes, and also the hydrodynamic mobility. So they actually much faster. You see that sort of like a intuitive, right? So then because of sharp is actually edges see each other, so they actually have enough room for fluids is actually expelled as compared to this case. So then actually the much less as the particles can be mobile much better here compared to the face-face. So these two interaction is really but this one is how the configuration changes when they actually move each other. So that actually brings the sort of concept of anisotropic nature of the particle interaction. So then is that this one is exemplified with this anisotropic interaction. In the colloidal literature, you can calculate stability ratio, but all stability ratio is based on spherical particle. So we exactly follow just the approximate spherical approximation, sort of like a hydrodynamic radius, something like this, to calculate using this interaction known for. But we can also measure from DLS this what is stability ratio experiment. You do see here in both reaction limited, especially reaction limited, is huge difference. It's 4 orders of magnitude difference. This is log scale. So that actually means that this spherical approximation is not far from what is happening. So that actually is the way to show, oh, this anisotropic nature is actually quite important, which from the shape, anisotropic nature particle interaction, that actually gives rise completely different behavior in comparison to sphere in terms of aggregation. So that's another kind of the good example how the shape or some kind of details matters for the aggregation phenomena. So that's the one. And then there's somehow the sort of last one is something like this. So then what is actually interaction, these changes for the macroscopic rheological property? So this is really like a practical aspect, but it's very important aspect here. So then to do that, as I mentioned the interaction is still very complicated. So we actually use the scaling analysis. We didn't really do that really like a quantitative interaction because this interaction, the colloidal interaction, hydrodynamic interaction between two non-spherical particle other than ellipsoid, and then rod, which is sort of very conventional one, and then probably a little bit of the information available for the platelet particle. Other than that, this non-spherical, these kind of the particle, for example, this kind of particle is not actually exist at all. So we still actually use some kind of spherical approximation to really like connecting this, but is also this because of there is a more the possibility for the simulation part. So we use the simulation method to actually really understand these connections. So what we are using is called the LFDEM. There's a lubricated flow discrete element method, which is sort of similar to the Stokesian dynamics, but because of the Stokesian dynamics for the many bodies, it actually takes a lot of time. So to really accelerate time scale for the calculation, we use this method. What is this method is actually ignore the particle inertia and solving the force balance equations. But at this force balance, we have a hydrodynamic force, which mainly we focus on short range hydrodynamic force, which is lubrication force. We ignore the long range hydrodynamic force, which is not really dominant for this aggregation and then rheological properties, although they will sometimes, but it's actually then Brownian force, depending on the particle size. And then this contact force, which is mimic or implement the surface roughness. When the particle is smooth enough, there is no contact because they contact one point, right? Very, very one point, but it's actually have a roughness. They actually somehow rougher surface giving some kind of contact areas that actually giving some significant contact force because sure, trying to move particles, this particle, but as a contact is really locking essentially, that gives a huge the force associated with contact force. So as we call the contact force, this is coming from discrete element method. Another one is repulsive, is electrostatic, and then the cohesive is another way to call this the van der Waals force. So we have this force. This is actually the called contact force, which have especially there's a lot of contact force in the tangential way. So that is actually really big the contact force. So by using that, we've observed many interesting phenomena. We can do that. So it's like a viscosity changes of the Peclet number, in this case, shear rate or shear stress. So that depending on the attractive force strength. So we have a large attractive force. This one is a slope is -1, you see here. That's actually a signature of the yield stress. The yield stress. So we see the yield stress build up. So then after certain time, as we don't really see the yield stress in it, depending on, so then the so-called related Hamilton constant essentially. And then in the very large attractive force, we don't only see the shear thinning, right? Viscosity decrease, but at a certain point, and like as we reduce the Hamilton constant, the attractive force, so the increase in viscosity. Here is more very clear. And another one we could do is actually the volume fraction. If we actually mix two different size particles, so what is actually the viscosities between them? Depending on relative, there's actually amount of two different size particles. So that's actually also, we can actually simulate using this kind of scheme. So this is a way to actually predict the rheology and including a lot of yield stress as a function of different, because these parameters essentially are related to the physical chemical properties of system. So then what we try to do is this. So we have surface roughness, which is actually, as I mentioned, very typical, and then essentially intrinsic, inherent nature of the minerals particle. So then as we actually mimic this as a contact force, as I described. The contact force is mathematical parameter, which we are not still, is not actually how to really we don't have a rigorous frame, how to connect mu to this real measurement of the roughness, such as mean square of surface roughness type of thing, how to actually connect these between this. We are still working on it, but it's actually, we have a mu parameter, which is mu 0 is no roughness, and mu is 1 is sort of like a normal, like a typical roughness. So what we can see is very interesting. So if you do that in the same strength, for example, red, which is actually has a relatively low attractive force, you do see not too much the difference in up to that reasonably large shear rate, and then start to deviate at a higher shear rate. But as the higher shear rate is something like this, 1/2 keep decreasing, right? So that without any, the dashed line is without any contact force, which means roughness. So then there's no, but it's actually have increase. So the shear thickening is due to that is the roughness. So then shear thickening is actually really driven by this roughness. If you have a higher the attractive force, you do already see something different here. And then another is the same thing as actually this, the without roughness is actually keep decreasing, but it's actually interesting to see the same goes the same viscosity, but actually then with the roughness, they start to see but it's a no shear thickening because of the high the attractive force, but it's actually very different behavior in terms of viscosity at high shear rate. So these one, if you actually look at a little bit more details on the network, how they connecting each other, this is actually related to contact network. So you see that this red is actually the network structure between particle. We can actually also observe from this simulation, because we know the position data a lot. So if you actually analyze a little bit further, where you can see this, the viscosity is what are actually contribution from each component. So the hydrodynamic interaction, van der Waals interaction, contact force, this is total. So it's like a contact is really dominating for this. In this case is about this or larger attractive force is really dominating to determine the viscosities. So this also related to shear thickening. So this is also we are trying to do the connect, so that this roughness in this case is about the 2-3 nanometer. In terms, we measure that using AFM. So this one, although it's particle size, and in this case is particle size, we are dealing with about the 100 nanometer or tens of nanometer. So the roughness is very small, but it's actually these influence really significant and the large scale phenomena, which is rheological responses. So this is also is good example. So that's why I put it in here, is a connecting to details, really details in the sort of like a atomistic scale to that macroscopic rheological responses. So those are essentially like a sort of overview of my talk. So then basically summary here is key message is this. So the colloidal dispersion is essentially the multi-scale natures implicitly, inherently. So then to understand this multi-scale nature and then how they connect between each other, so it's like a microscopic detail such as solvent structures and then shape and roughness, which is about particle scale, but we can actually really understand or at least getting better understanding for the larger scale phenomena, aggregation pattern, and then even this the fractal dimension, and then the rheological properties. So you see here, really like a details here, and then even talked about ion specific nature, but is they're using that as some kind of theory and then concept, which I actually showed that is the van der Waals interaction changes a lot due to this solvent structure, and then try to get some understanding is what's actually going on in larger scale and so-called collective phenomena. So that's essentially like a basic theme or the theme or many of the researches with collaborator is ongoing. So these are, I mean, obviously this research is not done by myself. Is actually having a lot of good collaborators and we are keep talking and discussing together. So here is a PNN collaborator. So it's like a Chris and Greg and Jim Diorier and Dongshang. And also there's the Jaehun and the Elias. So then also there's a non-PNN collaborator, especially Jeff Morris for the LFDEM. And then Jim Fenton and UW is about this, like a molecular simulation part of that. So then this is the funding from the particle interaction part, which I sort of like putting all my ongoing research together here is from DOE and BES material program, and aggregation from is actually called the BES, the EFRC iDream program. So thanks for the attention. I'd like to hear any of the comment and or any questions. Thank you.
Thank you so much, Dr. John. John, I think we have time for one or two questions. Is it right?
Yeah, that's fine. Yeah, we do have a.
Okay, but John, by the way, John has a question for you, Dr. John. What about John? What about you ask him question orally? Yeah. I know that you put some in the chat function.
Yeah, put something in the chat window, but maybe I could just expand on it a little bit. You have a very interesting presentation here where you've shown experimental results, but also very detailed multi-scale, multi-temporal modeling. And it seems like the two, you've done a very good job of kind of merging the two, where you're using experiments to help inform some of your models. But I'm just wondering about some of the models, such as, you know, the Clausius-Monsati and Onsager's model. And all of those rely on kind of a fundamental base, but then you have some unknown parameters that you might be fitting. I was just wondering, can you think about experimental results, how those could potentially create new models of some of these force interactions or field interactions? I'm thinking, you know, I mean, some of the new developments regarding big data and machine learning.
Yeah, so I think there's, I think the one, sorry, oh yeah. So sometimes I need to wake up my computer. So I think there's the machine learning side, since you mentioned that. So I think this is one of the good example. So this is collaborator, excellent collaborator. His name is called Dongsheng Li. And then she measured and fabricated and then measured. So you see, this is typical data for the force measurement. I just printed that. So these one have a lot of noise in it, right? You see that this noise is essentially related to the fluctuation of the system. So these noise we believe there is an important contribution from the Brownian motion. So we could actually, if we actually separate this noise from this real, this one is combination of short time behavior as well as long time behavior, which is typically we call the particle interaction is long time behavior, but there's a lot of noise, which is Brownian motion. So I think that's one of the important thing here is if we actually do this machine learning kind of the concept here to really extract two different components in it, so then is actually we could really understand what are really is like a little bit more deeper than this just the force measurement itself. Is actually getting some more statistical understanding to get this. What are short time scale behavior? How does the van der Waals, Brownian force in this kind of in this system? So is the well-known, is that compared to the well-known knowledges, or this is actually involving a lot of confinement? What we're talking about, the separation is about 1 nanometer or 2 nanometer. So then what are those? How these actually compare to the known theory? So that's actually one thing I believe is actually could be potentially influential from this machine learning process. And then another one is this experiment, I didn't actually really thought about this, but it's actually, this is one a good example between intercommunicate, sort of communicate each other. So this is experiment brings this together. So then is actually, I can't explain anything with conventional theory. So then we actually need to solve, what about these ions and details, which actually brings all about this. So then there's the putting into, that is the known theory of that. So then getting back to this experiment result. So then is that this is sort of like a one way, right? From experiment to the theory. And then we actually push back. So this is actually coming from pushback. So initially was experiment is this. So then it's, if that is a true, we might have a difference in divalent cation type of thing. So then we could actually push back into that experiment list to actually really getting some consistent story as well as some kind of the theory, and then also experimentally proven each other. But I actually, yeah. So as I mentioned, this is actually really one kind of the area where the machine learning part is actually really going to play very well.
Thank you so much. So yeah. I think we can have one more question, one more quick question. Is there anyone who would like to ask questions? All right. So if there is no question, let me ask you a question. So
yes,
you talked about effective roughness. I have a lot of questions about that, but one short question here is, if you have a hydration in the particles, don't you think you're gonna get do away with the roughness? So right now you're in this slide, you have an F contact force. Do you expect that F contact gonna decrease because of hydration? So one of your AFM experiments show during your AFM experiment, you told me that because there's a hydrogen layer, it's not actual mica-mica contact. So what do you think?
I think that if you have a hydration layer, I do see this one is step, right? So I can't really like draw, but if you have this kind of the pattern, like this is typically the mineral has a step kind of the roughness. So you have like a protrude region. So suppose we actually imagine there is a water layer here and here. So the up and bottom. So then really the separation determined by the not contact is actually the region between the protruded region from each other. So whereas some kind of the other way is actually, we don't really like, it's far away, right? So then this, obviously the roughness is actually play with this, the ion hydration layer. So what we are actually doing is right now, I didn't actually present. So what if actually we include the roughness combined with this concept? So then how these actually, all these picture changes. So that's actually what we are ongoing discussion, ongoing research right now. Because this one, you see the mica, so we don't really need to worry about roughness at all, because this is the world's most famous smoothest particle, right? But this, when we deal with this kind of particle, so it's like a, yeah, so if this kind of particle, so we need to consider that. In fact, the data already shows like this measurement data, you see decrease, right? So if you actually have a rough surface, we saw increase. It's completely different. So we actually trying to include that, how the roughness combined with this concept to explain this different, qualitatively different different data. So how to explain that? So that's actually really like an ongoing.
Yeah, I'm very interested in that.
Yeah.
All right. Thank you so much for presentation. Thank you everybody joining. So please thank Dr. Chun if you have a chance with your, you know that you have a Zoom function.
Yeah.
So yeah, thank you so much, Dr. Chun.
Okay, thank you.
Thank you.
김 박사님.